Okay, we are ready for the third speaker of today afternoon, with Alan Chigoli. He will talk about Fibred theory of obstruction and classification of morphisms. Please, Alan.
Okay, first of all, I'm very, very happy to be here on site at this conference. So many thanks to the organizer. Not only official ones, also all those people that made this event possible, because it was missing. Of course, thank you very much to the scientific committee for giving me the opportunity to speak of this work, which is a joint work with Sandra Mantovani, Beppe Mettere, and Enrico Vitale, which we would like to dedicate to Renato Betti on the occasion of his 80th birthday. I hope it Okay, so the starting point of this work is Schreier-MacLane theorem on the classification of group extensions with non-abelian kernel. What does it says? Given a group extension of kernel of non-abelian kernel K, conjugation in X gives an action on K, and since the image of K factors through the normal subgroup of inner automorphisms of K, there is a canonically induced map phi from the kernel Y to the group of outer automorphisms of K. It's just the quotient. And this map is called an abstract kernel of the extension. Each abstract kernel is a map of this kind. Determines an element in the third cohomology group of Y with the coefficient in the center of K, where the action is induced by phi. And so what Schreier-MacLane theorem says is that, first of all, an abstract kernel phi is associated with an extension, if and only if this element is trivial. Sorry. Thank you. And second, if this is the case, then the set of equivalence classes of such extensions inducing phi is a simply transitive set where the acting group is the second cohomology group with the same coefficients. This is classical. You can find it in the book of MacLane, homology. So now there are two apparently unrelated generalization of this result. The first one is given by Segarra, Garcia, Garcines, and Ortega. And it's a Schreier-MacLane theorem about the classification of monoidal functors between categorical groups. Categorical groups are also called two groups. Those are monoidal groupoids where each element is invertible up to i's. So with each categorical group, one can associate a group pi 0G of connected components of the categorical group, and also an abelian group pi 1G of automorphisms of the identity object. And there's an action of pi 0G on pi 1G that makes it a module, a pi 0G module. So we have cohomology with these coefficients, and each categorical group determines an element in the third cohomology group with these coefficients. So what they proved is that given two categorical groups G and H and a morphism PQ between the corresponding module structures, or multiple invariants if you prefer, there is a monoidal functor from G to H inducing PQ if and only if this element constructed starting from KH, KG, and by suitable translations and co-translation induced by PQ, which is an element of the third cohomology group. So there is a monoidal functor if and only if this element is trivial. And second, if this is the case, then the set of isomorphism classes of such monoidal functors, again, is a simply transitive set where the acting group is the second cohomology group. That's why I call it a Schreier-MacLane type theorem. On the other hand, in 2008, Bourne, gave an intrinsic version of the Schreier-MacLane theorem, which is available in any bar exact category, which is also action representative. I'm not going to explain how he did that. Of course, it is important because it made the Schreier-MacLane theorem intrinsic, and it enlarges the context. But what I want to point out here is an interesting aspect, which is interesting for the development of our work. In his paper, Bourne considered non-abelian extension, regarded non-abelian extension as internal equivalence relations in the slice category over the co-kernel. And he was able to describe the action in the Schreier-MacLane theorem as an action which was constructed via composition of internal perfunctors between internal groupoids. This is very important because it is a fundamental interpretation of the action. So having this in mind, some years ago, Enrico Vitale asked this question: is there maybe a conceptual framework, a common conceptual framework for these two generalizations? And answering this question took a certain effort, I would say. So I'm going to outline the fundamental steps of this work. First of all, 2013, Mantovani, Metter, and Vitale proved that the profunctors considered by Bourne were of a special kind, which are called fractals. Actually, Bourne's profunctors were of even more special kind, but the important thing is that they are fractals. Why this? Because fractals provide a bicategory of fractions, in the sense of Planck, of internal groupoids with respect to weak equivalences. Equivalences are internal functors between internal groupoids, which induce isomorphisms on homotopy invariants. A normalized version of this result, which in fact came before, is given by butterflies between cross modules. And it was proved by Abad, Mantovani, Metter, and Vitale. I'm going to explain what are butterflies in a while. Here we're taking advantage of the equivalence between internal groupoids and groups and cross modules. But I want to take a step further even and describe it in terms of crossed extensions, which are also an equivalent category. So what is a crossed extension? It's an exact sequence of this kind where the middle arrow is a cross module, J is its kernel, and P is its co-kernel. And whenever I have two crossed extensions, I can take as morphism between them just commutative squares that are equivalent with respect to the actions involved. And those are morphisms that correspond to internal functors between groupoids. If you go through the equivalence, those morphisms correspond to internal functors. So we even have two cells. And this data organized in a two category, which I denote by XX underline. But we also have another choice, which is the following: to take diagrams of this type that are called butterflies, where This diagonal is a complex. This other diagonal is a short exact sequence. And there are further conditions which correspond to the definition of internal profunctor. And this data, butterfly compose, there are two cells also, and this data organized in a bicategory. What they proved is that there is a homomorphism of bicategories between XX and BX, which is a bicategory of fraction with respect to weak equivalence. And it is a recent result that this homomorphism of bicategory induces a functor which is in fact a category of fraction. Here, the domain of this functor Q is just the underlying category of XX. We just forget two cells. On the other hand, in the codomain, we identify isomorphic one cells. This is called classifying category. Okay. With this point of view of crosshead extensions and butterflies between them, another fundamental step was this paper of Beppe-Metre and myself of 2016, where we use exactly this point of view to prove a Sire-MacLane theorem for the classification of extension with coefficients in a cross model. Again, I'm not going to explain this result, but I want to focus on two interesting aspects of this paper. The first one is that in that paper we regarded the action as an instance of the following elementary result. If you take two objects x and y in a groupoid, then the set, either the set of morphisms between x and y is empty, or it is a simply transitive set with acting group given by the automorphism group of x. This is very elementary but very important in our proof. And the second aspect is the fact that both the domain and the codomain of this functor are Fibred categories over the category of groups. And in fact, Q is a Cartesian functor. Cartesian liftings are constructed by pullback simply in the case of morphisms, and in a similar way in the case of butterflies. I'm not going to explain. But the existence of such Cartesian liftings plays a fundamental role in the proof. But this was not the end of the story, because there are also off-Cartesian liftings defined there along morphisms of Y modules. So if we start with a crossed extension and with the morphism alpha of Y modules, there exists a universal filling of this diagram, which is called push forward, and this provides an off-Cartesian lift. But we have to pay attention because unlike the abelian case where the situation is completely symmetric, we have pullbacks and push-outs, and we have a vibration on one side and an off vibration on the other side. Here the situation is not symmetric. We only have off-Cartesian liftings when we take this alpha to be a Y module morphism. So it's not any morphism. So we had to understand how to fit these two properties together. This is very similar to what Ionedas did in his 60 paper on X and extra sequence, but it is not symmetric. So we had to find a new concept to take all of this into account. And this was achieved in this work by Sandra Mantovani, Beppe-Metre, Enrico Vitale, and myself, where we explained that a crossed extension in fact fit in a commutative triangle of functors, which has the following properties. F and G are fibrations, and P is a Cartesian functor. And for each object B of the base category B, if we restrict P to the fibers over B, this restriction is an off fibration. And crossed extension fit in the diagram of this type in this way. We take pi 0 as the forgetful functor to groups, which takes the, say, the co-kernel of the crossed extension. Of course, modus also forgets to groups. And this factor pi sends each crossed extension to its associated modus structure of Y on A. We call such a triangle fiberwise of fibration. And there are several examples of such. For example, internal fibrations are examples of fiberwise of fibration, but our notion is more general. To have an internal fibration, you have to add an additional condition, which I'm not going to explain here. Ionett's regular span are also examples of fiberwise of fibrations, and two-sided fibration are also examples of such. So finally, what is the main result I'm going to present, which is the result by the same authors. If we have a fiberwise of fibration with this additional property, which is very important, we ask that P, the fibers of this functor P are groupoids. If we are in such a situation, first of all, and we are given two objects, X and Y in X, and a morphism phi between their images through P, then the set of arrows in X from X to Y, which are mapped to phi, is non-empty, if and only if these two elements are isomorphic, and these two are obtained by suitable Cartesian and off-Cartesian liftings. And second, when this is the case, this set is a simply transitive set with Epting group given by the group of automorphisms of phi over star of X, which are mapped to an identity in M. Okay, I think it's we have to explain this by a diagram. So here on the left, we have our big category X. Here is M, and here is the base category B. We have two objects, X and Y. We have a morphism between their images in M. This morphism maps to a morphism in the base category, so we can lift. We can take a Cartesian lift in A with codomain Y. Cartesian lifting of this morphism in the base category. Its image via P is again Cartesian. So we have a comparison V, which is vertical with respect to G. And since it is vertical, we can lift it with the co-Cartesian lifting, with domain X. And thanks to universal properties of Cartesian and co-Cartesian liftings, we establish a bijection between morphisms from X to Y, which are mapped to phi, and morphism from phi lower star of X to phi upper star of Y, which are mapped to the identity of this object. This is the obstruction part of the theorem. The classification part, the simply transitive action, is obtained by applying the elementary result I mentioned before. So, but what happens if the fibers are not groupoids? If the fibers are not groupoids, then we can apply this result by Sandra Mantovani, Beppe Metter, and myself. It says that if P is a fiberwise of fibration over B, and if Q is the category of fraction of X with respect to the class of arrows inverted by P, or P vertical. If this category of fraction is locally small, then P admits a universal factorization where this triangle SGH is again a fiber-wise of vibration with groupoidal fibers. And this is precisely what happens when we take crossed extension. Because crossed extension, the fiber-wise of vibration associated with crossed extension is not groupoidal fibers. So we have to take this category of fractions, but we know how this category of fraction can be described. Those are equivalence classes of butterflies. And this new triangle, this triangle on the right, is a fiber-wise of vibration with groupoidal fibers. So we can produce a classification theorem, not with respect to morphisms, but with respect to butterflies. Okay. So this is essentially what I wanted to say. Here, there's a list of theorems that we can get from the previous result. Just read the list. If we are in a case where fibers are groupoidal, then, for example, we can get a classification of morphisms between extensions of groups within the kernel, or the same thing in a semi-abelian context. Or a morphism, a classification of morphisms of singular extension of unitary associative algebras in terms of Hochschild cohomology. But again, we have cases with non-groupoidal fibers, the case that I mentioned, but also classification of monoidal functors between categorical groups is obtained again in this way. And also classification of cross-bimodal butterflies, which is a version of butterflies for unitary associative algebras, of which we can also have a particular case, which is a Shai-MacLane theorem. Thank you.
Thank you, Alan, for your nice talk. So, any questions here online? Yeah, Martin. Okay, if you can open the. Okay, Martin.
Hi, thank you for a great talk, Alan. Can I ask you a question? Would you mind going back to the slide with the bicategory of fractions and the category of fractions with Bx and Bx? Excellent. Do you think that, like, do you use something particular about those categories for and bicategories for that result, or do you think that that could be shown like with some more generality?
Sorry. Could you repeat, please?
Like you have a bicategory of fractions and like on top, and from it you take the category XX and you do pi 0 if I got that right from Bx. So I guess my question is, do you use something particular of those bicategories, or do you think that you could play that game with just the bicategory of fractions?
Well, I think it's spatial, but I don't know. We were able to prove this in this spatial case. It's not general proof.
So you use something very particular about those bicategories.
Yeah.
Okay, cool. Do you have a reference for that result?
Yes, yes. For bicategories of fractions?
No, for the proposition.
Yes, yes. I have a list of references at the end. I can send it to you too.
It's on the archive.
Great. Thanks a lot.
You're welcome.
Okay. Okay. If there are no other questions, let's thank Alan again.